just going to go over 3.5 derivatives of trigonometric functions. First thing we're going to do is do a conjecture to try to figure out what the derivative of sine is. And I'm going to use my graphing calculator for that. So in my calculator, I'm in my graphing feature. You will have to make sure you change it back to a function from parametric. Because if you recall in 3.4, one of the last things that we did was look at this with a parametric. So you want to make sure that you do get back to here. Notice in y1 I put in my function, sine of x, which if you recall, the graph of sine of x looks like the following. Okay, so there's the graph of sine of x. So we need to make a conjecture about the derivative of sine of x. So I'm actually going to turn off the graph of sine and turn on the graph of the derivative of what's in y1. And see what happens whenever we do that. So you see very, very similar, but there are some differences here. So again, the red one is the derivative. If you can't quite tell the comparison, it might be a good idea to go back and graph the original as well. So let's go turn that first one on. So again, blue is going to be the original, the red is the derivative. So there's the blue. And then here comes the derivative. This is kind of snaking along, has basically the same kind of shape, but it's really shifted pi over 2 units to the left. And that's because the derivative of sine is actually cosine. So you can see a cosine graph, the cosine of 0 is equal to 1, which is what we have here. There are places where the sine and cosine are identical. Those are those places where they cross. But otherwise, you take the blue graph and you're shifting it pi over 2 to the left, or pi over 2 to the left, and you would end up with the graph in the right one. So, derivative of sine is cosine. The derivative of cosine is negative sine. And you'll find, as we look at the derivatives of the different trig functions, all of the co-functions, so cosine, cotangent, cosecant, they all are going to have negative derivatives. So all of the co-functions, their derivatives are negative. Derivative of sine is cosine, derivative of cosine is negative sine. And then that brings us to our first example. Both of these incorporate rules that we learned about in 3.3. In letter A, you have two functions that are being multiplied together. So you will have to use the product rule to find that one. And in part B, I have two functions that are being divided, so we would have to use the quotient rule. So for A, we want to find the derivative. So my dy dx is going to equal the first times the derivative of the second. Well, the derivative of sine is cosine of x. Plus the second times the derivative of the first. And then you can simplify this if you want to, although there's not really a whole lot you can do. Typically, though, this 2x will get shifted into the front. So instead of saying that this is sine of x times 2x, you'd say 2x sine of x. And that's really so that the 2x doesn't get incorporated into the sine, because the only thing you're taking the sine of is the x, and then the 2x is just multiplied by the entire term. So just be careful with that. Okay, and that brings us to part B, and this one is going to require a little bit more space, so I'm going to scroll and give myself some more room. We do have to do the quotient rule here, because I have two things that are being divided. So du dx is going to equal low d high, so the derivative of the top, which is negative sine of x, minus high d low, so the derivative of the bottom. Well, the derivative of the 1 is a 0, so I'm actually going to leave that out. So I'm looking at the derivative of negative sine of x. The derivative of sine of x would be cosine, so since it's the derivative of negative sine, that's going to be a negative cosine. And then that's all over low squared. There may be cases where you have to expand the bottom with this. You'll see there's a couple of homework questions where you have to use some weird trig identities. Remember, those are in your textbook. I believe it's page 570. It is in the appendix. It's like the second or third page in the appendix in the back of your textbook before the answers are stated. So you may need to reference that while you're going through these questions. So let's finish this. We do have to distribute the negative sign of x up here. So I'm going to have negative sign of x plus sine squared x. Then I have a negative cosine times a negative cosine, so it's going to be a plus cosine squared of x. And that's all over 1 minus sine of x squared. Well, if you recall, there is a pretty famous identity here on the top, and that is the sine squared plus cosine squared. Remember, that's equal to 1. So we can actually change that. And I'm actually going to take that 1 and put it out in front of the minus sine of x because of what I have in my denominator. So I have 1 minus sine of x all over 1 minus sine of x squared. Well, I can divide out the top with 1 on the bottom. So that's 1 over 1 minus sine of x. And this is an example why it's important to do those trig identities, because if you didn't recognize that sine squared plus cosine squared is equal to 1, you would not have been able to get down into that very simple format. So just something to keep in mind that is very common, especially when you have these quotient rule properties with us. Okay, next. And I will scroll so you can see the entire picture here. I'm going to look at the top. We have a motion of a weight bobbing up and down on the end of a spring. This is an example of simple harmonic motion. This is not going to be a huge part of our lesson, but it is something that I do want to address. So you have your weight hanging from your spring, stretched to 5 units beyond its rest position, which would be 0, and then it's released, and it's going to bob up and down. Its position anytime, at any time t, is going to be s equals 5 cosine of t. And I'm actually going to write that down here. So you have the spring, and it's bobbing back and forth, as you can see here in the picture. So this is our resting position here at 0. The picture on the right is it being pulled down to 5 units beyond its resting position, and then it's going to continue to bounce. So it's going to bounce 5 shorter than its rest and 5 greater than its rest. And we want to know the velocity and acceleration. Well, velocity is the derivative of position, so we would take the derivative of 5 cosine t. The derivative of cosine is negative sine. Multiply that by the 5. So that's going to be negative 5, not cosine. These do switch. Negative 5 sine of t. If I said cosine there, I apologize for that. Derivative of cosine is negative sine. Negative sine times 5 is going to be negative 5 sine t. That is your velocity. Your acceleration then is going to be the derivative of velocity, or the second derivative of position. The derivative of sine is cosine. So we multiply the cosine by the negative 5, so it's going to be negative 5 cosine of t. So there's my velocity. There's my acceleration, and then we want to describe the motion. Now, this is one of those perfect world math type questions because there's no force acting on the spring other than the initial force where you're pulling it down. We're not worried about friction. We're not worried about it eventually coming to a stop again. So this is just going to keep bobbing between negative 5 and 5. So it's just going to keep bobbing up and down in between negative 5 and 5. For that last one, page 145 in your book does have a better explanation of the motion for that. So if you want to see all the technical stuff, that is in your textbook. If you have a change in your acceleration, that's what we call a jerk. And I believe this is something that I had referenced earlier in class, because somebody asked about if there were, what was the meaning of finding multiple derivatives. Well, jerk is what we call a third derivative. It is the derivative of acceleration, the third derivative of position. It would actually be the second derivative of velocity. So jerk is the rate of change of acceleration. Acceleration is the rate of change of velocity. Velocity is the rate of change of position. Jerk, rate of change of acceleration. So example 3a, the jerk caused by your constant of acceleration of gravity, so that negative 32 feet per second is going to be 0, because this is a constant, so when we take the derivative of the constant, we end up with 0. And this is why we don't get motion sick while you're sitting around on Earth, because there is no change to the acceleration of Earth. Earth is not, the gravity is not changing, it is constant, and that's a good thing, because otherwise you would get motion sick. This is why in a car, people typically get motion sickness. It's because they can't anticipate those changes in acceleration, and so when you can't anticipate that change, the body doesn't always respond appropriately. Now, part B, find the jerk of the simple harmonic motion. If you recall, the acceleration that we found there was negative 5 cosine of t. And so if you're going to find the derivative of that, remember the derivative of cosine is negative sine times the negative 5 that we have. And again, I'm going to so my jerk of the example that we had for number 2 is 5 sine. There are some things in your book to discover these other rules. Quotient rule is a very popular one because all of these can be expressed as quotients. For example, tangent is sine over cosine, so we could take the derivative of that using the quotient rule, but you would still end up getting secant squared as your simplified version. So tangent, secant, both of those have positive derivatives. Cotangent, cosecant, being the co-functions, both of those have negative derivatives. We kind of pair tangent and cotangent together though, because they both have something squared as their derivative, whereas secant and cosecant are two different terms, so secant tangent and cosecant cotangent. But you can see there's also a reason why we pair cotangent and cosecant together, because both of their derivatives involve themselves in the other. So whatever you need to do to memorize this, make sure that you tuck it away, make sure that it is something, maybe make a flashcard for it. We may do some IXLs on this later on just to practice, these particular, these derivatives, because they are something that you will have to memorize. Okay. Now we have example 4. We're going to find the equations for the lines that are tangent and normal to this graph at x equals 2. This will require a calculator, because it's not something you can find exactly because you have the tangent here. So I'm going to get you to a point where you would be plugging things into the calculator, and then I'm going to give you the numbers for those. So just, if you have any questions, please reach out to me if you're not quite sure where we get some of our answers from. So in order to find a tangent and normal line, I need a slope. And for a slope, we need a derivative. Tangent x over x is a quotient, so I have to use the quotient rule. So we have low, d high. The derivative of tangent is secant squared. Minus high, d low, all over low squared. That looks kind of ugly. There's not really anything that we can do to simplify that. So at this point, we would just plug in 2. So I'm going to evaluate this at x equals 2. So when you replace all the x's with 2's, you are going to end up with a rounded number of 3.433. To do secant, you would do 1 over cosine, and then you would put that in parentheses and square it. That would get you your secant squared. So now tangent. I'll do tangent line down here. We need a slope, which we have. We need an x value, and we need a y value. So in addition to having this 2 up here, I also have to find f of 2, which is going to be tangent of 2 over 2, and that is going to equal negative 1.093. So that's something you would just put in your calculator. And also make sure that you are in radians and not degrees. Whenever you're going through doing this, if you're in degrees, you're not going to get the correct answer, either for the derivative or for finding the function value. So tangent line, y equals 3.433 times x minus 2 plus, or rather minus, because it's a negative, 1.093. And so that is going to be, actually you can just leave your answer like that. That's how I have my answer left. You could go through and simplify your decimals, but you don't have to. You can always just leave it. Now for the normal line, I do have to find the negative reciprocal of my slope. So that's going to be negative 1 over 3.433, which is going to give me negative 0.291. Because you do need to have a perpendicular. It's negative reciprocal, so I take that 3.433, divide it, or 1 divided by that, and then change the sign, so negative 2.91. So my normal line is going to be negative 0.291 times x minus 2, and then minus 1.093. And again, you can leave the normal line set up like that. You don't have to go through and distribute that. Remember, you can always store your variables if you need. If you need to find something exact and you're worried about this, you can store these as different variables and you can work out the equation that way as well. Okay, last thing we are going to do, we're going to find the second derivative. If our original function is secant. So my y prime, the derivative of secant, is secant x tangent x. The derivative of secant is secant tangent. And again, if you recall, that was in the upper right-hand corner. It's not a cofunction, so it's going to be positive, and it's one of the ones that's in the column where it uses the 2 terms. Now to find the second derivative, we now have a product rule. Very simple to get the first derivative. Second derivative is going to require a little more work. So I have the first term times the derivative of the second. Well, the derivative of tangent is secant squared. And then plus the second times the derivative of the first. Well, the derivative of secant is secant tangent. And we can go ahead and clean this up a little bit. I have secant to the third of x plus secant of x times tangent squared of x. We can go ahead and factor out of secant. That might help us find some kind of connection here. So I have secant of x times secant squared plus tangent squared. And if you recall, we had some different identities. We don't actually have an identity for secant squared plus tangent. We have one for secant squared minus tangent, but there isn't anything we can do with plus. So this would actually be your final answer. Usually when you get down to this type of situation, there is something more that you can do with it, but this one, there's really nothing. Because that happens, you could actually leave your answer like you have here, and without factoring out the secant, but either are technically correct. This is your homework assignment. This is already in Schoology. It is due on Monday. Work through this. do the best that you can with it. I know some of the ones in the beginning section of odds can be a little bit weird because you do have to use some of the identities for those. So please reach out to me if you have any questions. Otherwise, we'll discuss this next week.